Today, I'd like to walk you through a story of government incompetence from all sides of the political spectrum. A nation where innovation actually may be stifled by regulation. An utterly ambivalent popular media and public who for decades denigrated research spending and the technology sector, only to realise too late that the rest of the world had moved on. This is the story of why Britain doesn't have a space programme anymore. "50 years ago, a team of British engineers achieved something extraordinary. I'll show a real-time animation of the glorious 10 minutes Britain was a spacefaring nation while I narrate this section. Through the 1950s and 1960s, the UK had a surprisingly promising space programme. Of course, the UK isn't really an ideal location to launch from, or it certainly wasn't back then, so a partnership was established with the Australian government to set up a launch facility in the Australian outback near the village of Woomera. Throughout the late 1950s and 1960s, the UK made 22 suborbital launches from the Woomera site using the Black Knight sounding rocket. Black Knight was a testbed for ballistic missile technology. It was considered a highly successful launch programme. The Blue Streak missile, for which Black Knight was intended to be a testbed, also made 4 successful suborbital launches from Woomera, but it was never put into full production. Now, I've spoken before about the differences between orbital and suborbital flight, basically summarised as go orbital or go home. By 1964, a programme was approved by the UK government to use the findings and technology from Black Knight to develop an orbital launcher, Black Arrow. While we won't cover the full development history here, let's take a look at the unique configuration of Black Arrow, which allowed for an unusually low-cost launch system. In a previous video, I mentioned showing Imperial units on screen. I think some viewers took that as a dig at US viewers, which it was not. It was just me trying to make things as accessible as possible. Anyway, I'm in no place to preach about various countries' choice of unit systems, because the UK has a truly cursed history when it comes to that. The UK only officially became metric in 1971, the year Black Arrow reached orbit. All the primary material is in imperial units, or a mix between imperial and metric, which is actually worse than trying to do rocket engineering in imperial. So, I'm just putting my foot down in this case. Everything's going to be in metric for this video. The most notable feature of Black Arrow, putting aside its physical appearance, was the choice of propellant. Any liquid-fueled rocket capable of getting a payload to orbit needs to combine and ignite fuel and oxidizer, which we collectively refer to as propellant, in a combustion chamber. The engines used by Black Knight and subsequently Black Arrow were part of a lineage derived from those used in the German Messerschmitt 163. This was a last-ditch late-war desperation weapon, a rocket-powered interceptor designed to shoot down Allied bombers. Like most Wunderwaffe, it was a particularly ridiculous design, even if it was reported to have surprisingly good flight characteristics. Though technically impressive, it could be argued that the 163 posed more of a threat to its pilot than to Allied aircrew. We all know the scene at the end of Raiders of the Lost Ark with the melting Nazis. Let's just say that actually pretty much happened at least once. That's because the 163 used hydrogen peroxide as its oxidizer, specifically high-test peroxide, which consists of about 90% hydrogen peroxide and 10% water. You may think of hydrogen peroxide as something for bleaching hair with, but that's 10% hydrogen peroxide at most. High-test peroxide, or HTP, is a really rather unstable compound as it wants to dissociate back into water. It therefore has the tendency to spontaneously and violently decompose in the presence of anything combustible, or a suitable catalyst. But the decomposition doesn't just produce water. 2 molecules of hydrogen peroxide decompose into 2 molecules of water and 1 of oxygen. So hydrogen peroxide, when used properly, can act as an oxidizer for a combustion reaction. From this point onwards, I'll refer to HTP, peroxide, or oxidizer interchangeably. They all mean the same thing. By the late 1940s, engineers at the Royal Aircraft Establishment had developed their own engine from that of the ME-163. And in 1952, the Armstrong-Siddeley Company had further developed this into the Gamma engine. This used a silver catalyst to decompose the peroxide before combining the reactants with a kerosene fuel source. The Gamma was further developed into the Gamma 201 and 301, which were used in Black Knight, and eventually into the Gamma 8 and the Gamma 2, used on the first and second stages of Black Arrow respectively. The major disadvantage of using hydrogen peroxide as the oxidizer is reduced performance. Since the combustion reaction requires oxygen, liquid oxygen is always going to give the best performance per kilogram carried. Okay, that's not actually technically true. Oxidization doesn't actually require oxygen. But liquid oxygen is the best performing oxidizer unless you want to fuel your rocket with something absolutely terrifying, such as fluorine. Hydrogen peroxide decomposition produces only about 47% oxygen by mass, with the rest being water. Engine performance for rockets is generally measured in specific impulse. We can think of this as a measure of the increase in momentum imparted to the system per kilogram of fuel carried. So a higher specific impulse means a more efficient rocket. For two equivalent systems, a liquid oxygen kerosene propellant delivers about 12% more specific impulse than hydrogen peroxide and kerosene. It's less of a difference than I expected, to be honest, and that's partially because of the chemistry of the reaction itself. When burning fuel in pure oxygen, all of the vehicle's kinetic energy is derived from the combustion reaction itself. However, in the case of peroxide kerosene engines, the decomposition of the peroxide takes place at 900 degrees centigrade and produces water vapour. Every molecule of peroxide produces 1 molecule of water, which is also ejected from the nozzle, along with the subsequent combustion products. Not only does this increase thrust from the engine, but water is relatively light compared to carbon dioxide, the other major product from combustion. Lighter exhaust molecules exit the nozzle at higher speed, which results in a higher specific impulse. Not only does this reaction give a decent specific impulse, but it's also simpler to initiate. The thermal decomposition of peroxide produces oxygen and water vapour well above the flash point of kerosene. So the kerosene fuel needs simply be injected into the combustion chamber to ignite the engine. No complicated and failure-prone ignition system required. There are other advantages to using hydrogen peroxide. It's much easier to handle than liquid oxygen, which requires cryogenic storage, making fueling more involved and more expensive. And having a higher density than liquid oxygen means peroxide takes up less physical space. This means a smaller rocket, less air resistance, and therefore a modest performance improvement. Another benefit, if you can call it that, is the unusual method of flight termination. Most launch systems require shaped explosive charges to be installed on the tanks. These are detonated if the vehicle deviates from its designated course and poses a threat to people and property. However, in the case of Black Arrow, the inherent instability of the peroxide is exploited. A small tank of manganese dioxide was present in the first and second stages. This acts as a catalyst to decompose the peroxide in the same way silver does. To terminate a flight, a command could be given to pump this into the oxidizer tank, causing a rapid thermal decomposition and destruction of the vehicle. The distinctive bare metal look on the first and second stages was due to the use of a lightweight BS L73 aluminum alloy. The nose fairings were constructed from magnesium alloy. The design report also states that titanium was used where it could be employed to advantage. The material choice allowed for an ultimate design factor of 1.33 for flight conditions, which I find interesting. Launch systems typically operate on a design factor of 1.25. We should remember it's actually often cheaper to design a system with a higher design factor. Bringing it down, and therefore increasing payload mass, requires disproportionately more time the closer that value is to unity. Though lacking the specific impulse achievable from a liquid oxygen kerosene system, the 2 kerosene peroxide stages were sufficient to boost a payload to about 4.5 km a second, with a 600 km perigee. The final 3 km per second of delta V was achieved by a solid-fueled third stage. To reduce mass to an absolute minimum, the solid fuel was enclosed in a spherical stainless steel shell. There was no guidance system on this final stage. It was spun up on its longitudinal axis by small rocket motors called imps prior to release from the second stage. The spin stabilization ensured correct orientation was maintained during the 40-second third stage burn. The end result of all the above design choices was a tiny rocket by orbital standards. The entire Black Arrow stack-up was just 13 meters in height, with a launch mass of just 18.1 tons. It was also cheap. The entire decade-long program cost just £9 million. Converting that to modern-day money is subjective, but about $100 million in 2023 is a ballpark figure. For the uninitiated, that is obscenely cheap. However, it was capable of delivering a 100 kilogram payload to a 600 by 1000 kilometer polar orbit, easily sufficient for small research satellites of the early 1970s. As I like to say, any rocket that can get anything, even a single CubeSat, to orbit is a good rocket, and Black Arrow could do much more than that. In my opinion, the most interesting method for clawing back some specific impulse was the unusual combustion cycle used by the Gamma engines. I think it's worth going through the basics of their operation before we discuss the specifics of the design. Most liquid-fueled engines use liquid oxygen as an oxidizer, as previously discussed. This is mixed as close to the stoichiometric ratio as possible to ensure all the fuel is burnt as vigorously and completely as possible, increasing the chamber pressure, and therefore increasing the exhaust velocity to the maximum possible. The higher the exhaust velocity, the higher the specific impulse. Engines actually tend to burn slightly fuel-rich for reasons we won't get into yet, but in general, they're operated as close to the stoichiometric ratio as practically possible. I just referred to chamber pressure. The Gamma engines had a chamber pressure around 50 megapascals, which was actually relatively low. Modern engine designs have been known to exceed 300 megapascals. And this leads us nicely into quite possibly the most significant challenge when designing liquid-fueled engines. How do we get our propellants into the combustion chamber? We need to inject both the fuel and oxidizer at a pressure higher than the chamber, or they'll simply not flow in. The answer is to use pumps. There are different engine cycles. Before we get onto the Gamma engine cycle, we'll focus on the simplest relevant design, the open cycle gas generator. Here we see a centrifugal pump for each propellant line. These are capable of taking low pressure propellant from the tanks and increasing the downstream pressure to above that of the combustion chamber so the propellant can flow in. But how do we drive these pumps? Obviously, given the volumes and pressures necessary, a significant amount of energy is required to spin them up for the duration of the engine burn. Fortunately, we're already carrying something extremely energy dense: rocket fuel. In an open cycle engine, we divert a portion of the fuel and oxidizer and burn it in a separate mini combustion chamber, or gas generator. This produces a high pressure exhaust that can be used to spin a turbine. Connect this turbine to the propellant pumps via a common shaft, and we've just powered both of our propellant pumps. a turbine and pump arrangement, aka turbopump. This is very much a tried and tested arrangement, and is the cycle responsible for delivering the majority of payloads to orbit. However, there's room for improvement. First, the requirement for a gas generator, which necessarily operates at high temperature, adds complexity and cost to the design. Likewise, the high temperature exhaust demands a turbine capable of operating under exceptionally strenuous conditions. Imagine driving a turbine with a gas welding torch. That's almost what's happening here. For context, the turbopumps used on Black Arrow were required to output about 700 kilowatts each, which is the energy equivalent of about one stick of dynamite every 1.5 seconds. It's easy to see why rocket turbopumps are some of the most researched design problems for mechanical and materials engineers. To reduce the turbine temperature to below welding torch levels, open cycle engines run the gas generator fuel rich. This, however, introduces an inefficiency. The spent exhaust contains a non-negligible amount of unburnt fuel. So, when using an open cycle engine, we're never able to burn all the fuel available. And considering the already feeble fuel-to-payload ratios needed to reach orbit, that leads to a significant reduction in payload. Every kilogram of fuel that goes unused equates to a loss in payload mass. The solution to this is to pass the exhaust into the combustion chamber so we can burn that unused fuel. Simple, right? Wrong. This is called staged combustion, and is one of the most difficult problems in rocket engineering. It's been done several times, but it requires incredible complexity for reasons that we won't get into now. Now let's take a look at the cycle used by the Gamma engines. I've never actually come across a name for it, so I'll just call it the HTP open cycle. Here, directly above the combustion chamber is a catalyst pack, composing of layers of silver-plated wire mesh. Recall that hydrogen peroxide violently decomposes into water and oxygen in the presence of silver. So we pump our hydrogen peroxide in through the catalyst. To drive the pump, a small fraction of the peroxide is diverted prior to entering the chamber. However, it does not go into a conventional gas generator. Instead, it's passed into a steam generator. Again, this is essentially a miniature version of the combustion chamber, complete with a catalyst pack. However, no fuel enters this chamber. None needs to. The high-pressure steam from the decomposition of the peroxide is easily sufficient to drive the turbine and pump the peroxide. At this point, we actually have a fully working rocket engine. This design is referred to as a cold peroxide engine, as it doesn't actually burn anything. This cold cycle is certainly capable of producing thrust, but not enough to get to orbit. So, as with the open cycle engine, we add in the fuel line with its own pump connected via the common shaft. The fuel bypasses the catalyst pack and is combined with the superheated steam and oxygen in the combustion chamber to ignite and therefore produce thrust. We can see this is sort of a half-closed cycle engine. We don't need to waste any unburnt fuel in order to drive the turbine. However, we do exhaust some oxidizer overboard. Now, compared to a conventional open cycle engine, it'd be relatively easy to feed the dissociated oxidizer back into the chamber and achieve a true closed cycle. Due to the lack of accessible information on Black Arrow, it's widely believed the Gamma engines operated on a closed cycle. However, that is not true. It wasn't possible due to budget constraints. So they operated on an open oxidizer cycle, as shown here. But we'll revisit closed cycle peroxide engines at the end of the video. In the case of Black Arrow, the partial efficiency gain was just one advantage of its unusual engine cycle. The 900-degree steam used to drive the turbine was cooler than the working fluid in a conventional open cycle engine, simplifying the turbine design and requirements. And the lack of a fuel oxidizer gas generator also simplified the design and cost. And of course, it reduced overall mass. To understand how this cycle was applied on Black Arrow's engines requires some context. Black Arrow used a Gamma 8 engine for its first stage and a Gamma 2 for the second stage. The most detailed schematic of any Gamma engine I could find was this drawing of the Gamma 201, showing a combustion changer and the turbo pump. The Gamma 201 was used in Black Knight and was a precursor to Black Arrow's engines. I've highlighted the relevant parts here. Note, the peroxide flows through the hollow nozzle before passing into the combustion chamber. This regenerative cooling is standard in liquid-fueled engines. Not only does it prevent the nozzle from melting, but it preheats the oxidizer, allowing it to decompose more completely. In most designs, the fuel is used for cooling, but hydrogen peroxide is more conductive and has a higher specific heat capacity than kerosene. This was yet another advantage to using hydrogen peroxide as the oxidizer. The 201 was upgraded to the Gamma 301, used in the later Black Knight flights. This diagram shows the thrust chamber for a 301. The most notable difference is the regenerative cooling method. The dual-wall nozzle and thrust chamber design was replaced with 60 stainless steel tubes. Peroxide was pumped into alternate tubes, flowed to the manifold at the base of the nozzle, and returned back up the intermediate return tubes. So, with that, we can now move on to the Gamma 2 engine used in Black Arrow's second stage. Here we see a Gamma 2 thrust chamber, which was largely similar to the 301 that I just showed. However, there are a few interesting differences. This engine was designed to perform in the vacuum of space. When designing a nozzle for a rocket engine, we endeavour for the gas at the base of the nozzle to be as near to ambient pressure as possible. This gives the escaping gas the maximum possible space to expand, and putting it in simple terms, push back on the nozzle, and therefore the vehicle as a whole. In a vacuum, the ambient pressure is zero. So we make our nozzles as large as possible until weight becomes an issue. So, the Gamma 2 engines had a nozzle extension. When we look at modern-day two-stage rockets like the Falcon or the Electron, they tend to use the same engine for the first and second stage, but with a vacuum-optimised nozzle on the second stage. One engine design for lower overall costs. Remember, Black Arrow was designed on an absolutely minimal budget, so this principle of a single engine design was taken to a particularly interesting extreme. The nozzle extension was essentially a bolt-on, with the thrust chamber itself being identical to those in the first stage. But then how to cool the nozzle extension? The peroxide was already being used to cool the chamber itself, and the pressure and flow rates had already been optimised for this design. But the fuel was still available for cooling. There was much less of it, but the cooling requirements for the nozzle extension were less than for the combustion chamber. So, unburnt fuel was first circulated around the extension before being injected into the combustion chamber here. The Gamma 2 had two such chambers, both sharing a single turbo pump, which is in the centre of the diagram, but largely obscured. We'll take a closer look at turbo pumps in a second. For now, let's look at a final interesting design choice for this second stage engine. The high-pressure fuel flows out of the fuel pump here. Before reaching the thrust chambers, it enters this manifold and pressurises these lines. These are hydraulic lines. The two chambers could be individually gimbaled to allow for steering. This was achieved through the use of hydraulic rams, which actuated the chambers. However, instead of using hydraulic oil, the fuel itself was used as a working fluid in order to save mass. The use of fuel as hydraulic fluid isn't unique in spaceflight, but it's just another small saving Black Arrow's engineers were able to implement to bring the vehicle's mass down enough to reach orbit. Putting together everything from this chapter, we finally get to the first stage engine, the Gamma 8. Engine used singularly is debatable here. The Gamma 8 consisted of 8 thrust chambers mounted in pairs. Drawing a diameter across the base of the rocket, splits the system into two largely independent units, each sharing one turbopump. They also share one fuel mixture controller and one turbine exhaust. So whether the Gamma 8 was actually 1, 2, 4, or 8 engines is a matter of linguistics. Unfortunately, this is the best schematic I could find of the engine. It's pretty terrible, but through a combination of persistence, colouring in a copy with my son's colouring pencils, and trawling the internet for reference photos, I've been able to figure out the general operation. First, we draw a line through the centre and only consider 4 thrust chambers, since the assembly is, for all intents and purposes, symmetrical. Here's the turbopump unit that feeds all 4 chambers. Oxidizer enters through a suction valve in the centre and is pumped to a high pressure via the oxidizer pump here. Most of the high pressure oxidizer flowed into the thrust chamber via the chamber cooling channels and then the catalyst pack, where it was dissociated. Some of the oxidizer was tapped off and fed into the steam generator, which I believe was integrated into the turbopump unit, so it's not visible in this schematic. The resulting high-pressure steam drove the turbine situated here, and was exhausted through this exhaust line. Unlike the turbopump shown in the Gamma 201 earlier, there was not a direct shaft between the turbine and the pumps. There was a gearbox. The fuel pump was driven on its own shaft from the gearbox here. Fuel was fed via an external line from the forward kerosene tank and into the pump. From here, it was fed into this mechanical mixture controller. This was essentially a carburettor, but it maintained the fuel and peroxide mixture ratio, and it did so to within 0.5% of accuracy. It operated by comparing flow rate from the fuel and oxidizer lines measured via the venturi here and here. Measuring the fluid pressure at a venturi of known dimensions allows us to infer the fluid flow rate. So, the fuel and peroxide pump pressures were passed to the mixture controller, along with the venturi pressures, and it was able to mechanically meter the flow of fuel in order to maintain a constant mixture ratio. The output from both flow controllers flowed into a common manifold to maintain a constant fuel pressure across the entire system. It was then fed directly into the combustion chambers. Finally, a smaller pump was driven by the gearbox to give pressure to the hydraulic system. Unlike the Stage 2 engine, this was a self-contained system, using hydraulic oil to actuate the thrust chambers. Chambers were actuated in pairs and could pivot on one axis only. However, when considering the 4 independent pairs of chambers, this was sufficient to control movement in the pitch, roll, and yaw axes. Though complex to explain, this unusual engine arrangement was simpler and therefore cheaper than the equivalent alternative, which would have been 8 independent engines. Each would require their own turbopump, mixture controller, and plumbing. The final result was a relatively cheap Stage 1 engine with an adequate performance for orbital flight. The technical report by the staff of the Space Department from 1969, which by the way is the main source of technical information for this video, states a sea level specific impulse of 217 seconds. That figure is in contradiction to the figure on Wikipedia, by the way. Another point of note, a Gamma engine never failed in flight. Of all 22 Black Knight and 4 Black Arrow launches, the engines performed flawlessly in every case. The final unusual design choice I'd like to discuss regarding Black Arrow is that of flight stability. Traditionally, and by traditionally I mean in the 1950s, rockets were designed to be inherently stable in pitch and yaw. This meant ensuring the centre of gravity was forward of the centre of pressure throughout the atmospheric phase of flight. The best way to visualise this is to think of a shuttlecock. Most of the aerodynamic force is towards the back, so if it starts to yaw in flight, the airflow on the feathers causes it to rotate around its centre of mass, which is near the front, and keeps it facing in the direction of travel. Building a rocket with the centre of pressure ahead of the centre of gravity is like trying to fly a shuttlecock backwards. It's unstable. This is why older rockets have large fins at the aft. They act like the feathers on a shuttlecock. However, they add drag, and therefore adversely affect performance. So, since the 1960s, most large rockets have been designed to be inherently unstable, with an automated guidance system able to gimbal the engines or actuate fins to keep the vehicle pointed in the direction of travel. However, it's still desirable to have the centre of pressure as far aft as possible. The further forward it is, the more the guidance system has to work to keep the vehicle on course. So, most designs put the heavier oxidizer tank above the lighter fuel tank to get as much mass as possible near the front. Black Arrow had a particularly large and heavy oxidizer tank due to the high oxidizer fuel ratio of around 8.5 to 1, and also the high relative density of the peroxide. So, the oxidizer tank was definitely at the top, right? No, it wasn't. It was the opposite. It sat below the fuel tank on both stages. I've not been able to find a definitive source for why this choice was made, but my guess is mass reduction. With the heavier oxidizer tank nearer the base, less structural material was probably necessary to prevent shell buckling. Also, consider the direct flow path from the oxidizer tank to the engines. With such a high oxidizer to fuel ratio, having the larger tank nearer to the engines necessitated smaller diameter pipes to the upper propellant tank, again reducing overall mass and cross-sectional area. In fact, using the data from the staff technical report, we can get a pretty good estimate on the location of the centre of gravity at launch. And the centre of pressure can be easily estimated too, using the old trick of balancing a card model of the rocket. This works because Black Arrow was pretty much symmetrical across all the longitudinal axes. However lenient I try to be, the centre of gravity comes out way ahead. Now, the two do move throughout flight. The centre of gravity has the tendency to move forward as the propellant tanks are drained. Centre of pressure is a little more complicated. It starts to move backward as the vehicle approaches supersonic flight, and then tends to move forward again as we go supersonic. But either way, Black Arrow was probably more inherently unstable than most launch systems. A month ago, I released a video all about digital fly-by-wire, and how it's able to maintain flight stability in inherently unstable aircraft. Black Arrow indeed had an automatic flight control system, a fly-by-wire equivalent, if you will. The system was necessary to maintain stable flight, and it was perfectly capable of doing so. However, it was entirely analog. We won't go into full details of this system here, but here's a simple flow diagram of it. The flight itself was pre-programmed in the flight program unit. This was a series of rotating cams on clutches designed to engage at various stages of the flight. The cams had engaged micro switches, and as they were switched, they'd switch the rest of the system to different modes depending on the stage of flight. An attitude reference unit, which was basically a series of gyroscopes and accelerometers, formed a stable reference against which accelerations and orientation could be measured. This was actually taken from a TSR-2, which is another project abandoned by the UK government. Although I tend not to shed as much of a tear over that one. It was a nuclear strike aircraft. Deviations from the pre-programmed course were translated into voltages, which were fed through a servo loop, eventually resulting in the hydraulic actuators gimballing the engines. For stage 2, after engine burnout, a similar process was followed, but using nitrogen RCS thrusters to maintain the correct orientation. A total of 5 Black Arrow rockets were built. 4 were launched, and 1 currently resides in the Science Museum in London. I walked past it many times when I was at university, but I wasn't able to fit a trip to London to film it before releasing this video. The vehicles were named R0 through to R4. The first 2 flights were suborbital test flights. R0 experienced roll oscillations as soon as it left the launch pad, resulting in an eventual flight termination. This was traced back to a broken wire between the thrust chambers and the flight control system. R1 launched successfully with a dummy payload. The first attempted orbital flight, R2, was very nearly a success. A leak in the oxidizer tank caused the second stage to cut out early, with the vehicle failing to reach orbit. R3 was a success. It delivered the X3 satellite to orbit. Though I can't find any definitive evidence, it's reported that the third stage fired a little too enthusiastically and collided with the satellite immediately after release, knocking off one of the radio antenna. Immediately prior to launch, X3 was renamed Prospero. This isn't an English literature-themed video essay, so I'll leave it to the viewer to discover why that name was chosen. Reaching orbit on a second attempt seems to be about the norm for modern-day launch systems. If anything, it was an indicator of reliability back in the early 1970s. Unfortunately, this never seems to have been effectively communicated to the British government or public, who either didn't really care about Black Arrow or had somehow grown to perceive it as unreliable. I think most viewers probably know where this is going now. Black Arrow never launched again. In fact, the program had been cancelled before the final flight even took place. It was simply decided that the cost of turning the ship around was about the same as just getting it to Australia and launching it. I'm not going to sit here and get angry about something that happened 50 years ago. In fact, I'd be preaching to the converted anyway. I imagine almost everyone watching this video agrees that cancelling the program was poor decision-making at best. But for viewers unfamiliar with British politics, the cancellation is actually quite easy to explain by summarising the 2 political parties in the UK, or the 2 major political parties, I should say. Much like the USA, we have a red team and a blue team. The blue team are the Conservative Party. Very broadly speaking, they're comparable to the Republican Party in the USA. They historically have been reluctant to fund public projects. Generally, something like a space program is the responsibility of the private sector in the eyes of many Conservative voters. The red team are Labour. There's no direct analogy for the Labour Party in the USA, but until the late 90s, they were very much the pro-worker and pro-nationalisation party of the UK, though they're somewhat watered down these days. They have a track record for more public spending, but generally wouldn't be seen dead funding anything which could be considered frivolous. And without the justification that no one is willing to sell to voters, nothing appears more frivolous than a space program. Even a cost-effective one run on a shoestring budget with potential for significant profit down the line. Technically speaking, both governments cancelled Black Arrow. The programme was instigated by a Conservative government under Harold Macmillan. Subsequently, it was put on hold for 2 years during the mid-60s by a Labour government under Harold Wilson, and it was finally cancelled by another Conservative government under Edward Heath in 1971. Completely unappreciated by MPs across the political spectrum. Remember, the cancellation of Black Arrow didn't just mark the end of the system itself. It effectively ended the British space programme altogether. Putting it in the context of other related projects somehow makes the cancellation even more absurd. To do so, let's visualise the full lineage on screen. It gets a little complicated. The other British rocket, which I briefly mentioned earlier, was Blue Streak. It was initially conceived in the late 1950s as a nuclear ballistic missile. It quickly became apparent it would not be suited for that purpose. But the project was kept alive on the promise of using Blue Streak as a first stage of an orbital launch platform. Recall, the British government had already independently funded the Black Knight sounding rocket. A Black Knight upper stage was to be incorporated onto a Blue Streak first stage to create the Black Prince. However, it was soon realised this system would simply be too expensive, and the system was never realised. It was at this point the smaller and cheaper Black Arrow system was first proposed. Oh, and of course there was the other British rocket, Skylark. This was a small suborbital sounding rocket, though highly successful, but it's largely out of the scope of this video, being suborbital. I mention it here because an upgraded Black Arrow with 8 Skylark strap-on boosters was proposed. Of course, that was never flown. But Blue Streak managed to live on. In seeking international partners for Black Prince, the project was revived as the Europa project. France was to develop the second stage, the Coralie, and Germany was to build the Astris third stage. Italy, Belgium and the Netherlands were also to make technical contributions, with the collaboration being named ELDO, or European Launcher Development Organisation. If you're wondering why there's a skirt at the bottom of the Black Arrow, that's because the rocket was sized to replace Coralie in the case the French dropped out of the Europa project. The skirt would have formed part of the interstage, with Black Arrow's first stage becoming Europa's second stage. Much as Britain were developing Black Arrow in parallel to contributing to the Europa project, France developed their own independent launcher, Diamant. That first launched in 1966. Meanwhile, 5 Blue Streak test launches were carried out from Woomera between 1964 and 1966. The first was a failure, but the following 4 were successful. However, less could be said for the full Europa stack-up. 6 subsequent tests with the Blue Streak, Coralie and Astris stack-up failed, in all cases due to the second or third stages failing. So, it is understandable that the British government decided to pull out of the Europa project in 1972. What is not understandable is their decision to go from having one orbital system and the only reliably functioning and largest stage on another orbital system to having nothing. Meanwhile, ELDO reformed as the European Space Agency. Headed by France, they went on to develop the Ariane family of launch vehicles, most recently the Ariane 5, arguably the most successful heavy launch vehicle of all time, with France retaining majority control of the programme. Britain remains a minority member of the European Space Agency, but can't really claim any stake in the development of Ariane or any other orbital launch system. Britain went on to launch its own satellites on the American Scout launcher under the assumption of it being cheaper, though the USA did rescind the offer of discounted launches to the UK once they learned we'd given up on our orbital space programme. No additional comments required from me there. The Scout went on to be the most prolific small satellite launcher of all time, to date anyway, demonstrating the rising demand for light launchers. Independently, Japan, China and India all launched their first orbital spacecraft between 1970 and 1980. In all cases, these nations went on to develop larger, medium and heavy class launchers, and all continue to maintain highly successful space programs to this day. The rest of this video is quite depressing, really. The 50 years following the cancellation of the British space programme have seen some attempts to relight the spark. All have faced the same headwinds Black Arrow faced. Consequently, most are dead and buried or stuck in development hell. We're going to look at some of the projects I grew up with and how I watched them wither, die, or zombify. This'll cover my own experiences, but we'll keep it as factual as possible, though I don't have time to go into extensive detail about every case. However, if you make it to the end of the video, I promise there's a spark of hope waiting. By the 1980s, I suspect the Thatcher government had realised the astronomical mistake their predecessors had made. The US Space Shuttle was rapidly increasing access to space for both cargo and crew, paving the way for the commercialisation of space. In an attempt to rejoin the party, a consortium of relevant British companies and institutions proposed a concept that was in many ways the polar opposite of Black Arrow: HOTOL. Where Black Arrow had been a modest, low-cost, but entirely realistic undertaking, this proposal was ambitious to the point of absurdity. HOTOL, a terribly constructed acronym for horizontal takeoff and landing, was to be an air-breathing, single-stage-to-orbit spacecraft. As I don't do in-depth analyses of things that don't exist on this channel, let's summarise it in a couple of sentences. The craft was to take off using jet engines and fly to the upper atmosphere, accelerating to at least Mach 5, which would make it the fastest crewed jet aircraft ever flown. It would then switch to rocket power, burning onboard liquid oxygen and fuel to raise and accelerate it to orbit. When it was time to return home, it would deorbit and land horizontally on a runway. It was soon realised the necessary technologies to make HOTOL possible were decades away. Specifically, first viable launch was estimated to be in the 2020s, and the project was, probably rightly, deemed too expensive to be viable. But hold on, it's the 2020s now. HOTOL ceased to exist as a program in 1989. But some of the co-creators went on to form the king of space vaporware companies, Reaction Engines Limited. I've grown up hearing occasional hype from this company. For almost as long as I can remember, they've been knocking out CGI renders of their proposed Skylon launch platform. Around the time I graduated, which was in 2011, there was a minor media buzz about their latest success, the engine intake heat exchangers. These are some serious engineering, cooling down hypersonic intake air to an acceptable intake temperature. At the time, it was stated this was the difficult part, and they'd achieved it. Since then, well, not much really. 12 years later, and they don't have a working engine, let alone any flight testing. Now, I don't want to criticise reaction engines personally. The economic and public relations climate in the UK is just not the place to develop a groundbreaking spaceplane design. I do understand they've received funding from DARPA in recent years. Who knows, maybe they'll produce something tangible one day. If they ever do produce something, I very much doubt it'll be British. If you went to school in the 2000s in the UK, there's a good chance you met this man. This is Steve Bennett, the founder and CEO of Starchaser. When I was growing up, this was about as big as rocketry got in the UK. To give them credit, by the late 90s, Starchaser had achieved a series of hobby-scale rocket launches that weren't to be completely scoffed at. They were able to get payloads up to about 7 kilometres. This is far short of space, and far, far, far short of orbit. Given enough funding and interest, maybe Starchaser would have eventually built something useful. I'm highly sceptical. But honestly, this was as good as it got back then. Starchaser were at least doing something. Regardless, they shot themselves in the foot. They decided to have a go at the Ansari X Prize. This is a competition that I've been critical of in the past. It was intended to promote private spaceflight. I argue it actually hindered it. $10 million for the first privately funded team to put a 3-person craft into space. Starchaser decided to, well, chase the $10 million. Going from a small 7-kilometre capable rocket to a crew-rated 100-kilometre model was ambitious. A famous BBC article highlighting the risks in Steve's proposed design effectively destroyed the company's credibility in the eyes of the few public that were taking interest. Probably worse still, with efforts focused on this new Nova-class rocket, Starchaser never again exceeded their altitude record of 7 kilometres. Much of their funding is now from public outreach. What that translates to is Steve driving his rocket around the UK on a truck and visiting schools to inspire the youth. In summary, Starchaser launched large hobby-class rockets to the upper troposphere. They still exist, but they don't really do much. Christmas Day of 2003 was the most miserable Christmas of my life. I'll never forget waking up, running over to the TV, turning it on, and seeing communication had been lost with Beagle 2. Beagle 2 was a prime example of the British government, academic sector, private sector, getting together and getting everything right, and then completely blowing it. Now, this video is about launch systems. Beagle 2 was an interplanetary probe, a lander for Mars, but the ambition was on the same level as something like Black Arrow. It was also a pretty pivotal moment in my life, so I'm including it. Beagle 2 was tiny, just a metre in diameter. It was to unfold on the Martian surface, deploying solar panels, a communication array, and various scientific instruments. It got so close. It made it to the surface, unfolded 2 panels, and then jammed, blocking the communications array and permanently condemning it to remaining silent on the Martian surface. When Beagle 2 failed to phone home, the project died. There was no follow-up. There was no push to take the valuable learnings from the project and apply them to something else. No one, government or otherwise, stepped up to fund a Beagle 3. And this was the early 2000s. The UK was not short of money back then. The screw-up wasn't the failure of Beagle 2 itself. That's part and parcel of space exploration. That should have been a setback. The real failing here was making that failure terminal. As one of the few British kids who wanted to be an engineer at this point, remember the acronym STEM didn't even exist back then. If you were good at maths in the UK, everyone told you to go into banking. No one wanted to be an engineer. It felt to me like the lesson to take away was, if at first you don't succeed, just give up. Or move to America. The story of Virgin Orbit is only tangentially related to the UK, but I think it serves as a final cautionary tale. Virgin Orbit were an American company. By early 2023, they had a mixed track record for their new smallsat launch system, the incredibly creatively named Launcher 1. At the start of this year, they planned to make, and imagine me making air quotes as I say this, the first UK space launch of a satellite. Now, credit where it's due. The Civil Aviation Authority had gone through the effort to facilitate the launch, and the UK Space Agency had provided some of the funding and assistance to convert a small airport on the southwest peninsula of England into a spaceport, as they referred to it as. And yes, spaceport is their words, not mine. To me, this always looked like a minimum possible investment from the UK government and industry to appear competitive in space. Launcher 1 was carried under the wing of a Boeing 747. Of course, this needed more specialised facilities than you'd find at a run-of-the-mill airport. Fueling, tracking, communications, and of course the safety considerations of handling tons of liquid fuel and oxidizer. But the launch, if you want to call it that, was just a Boeing 747 taking off from a runway to fly to a release point hundreds of kilometres offshore. That didn't stop significant press fanfare. The BBC ran a live page that day, honestly giving the appearance of desperately trying to hype up what was not really particularly eventful. Politicians arrived at the launch site, and our Prime Minister tweeted about the, quote, incredible work that had gone into the UK's first launch of an orbital satellite, end quote. He conveniently omitted the fact that the vast majority of that work was done by the USA, and depending on how you interpret those words, completely erasing Black Arrow from history. From memory, it really felt like we were trying to take credit for something we had virtually no involvement in. Anyway, the launch was a failure. In fact, it bankrupted the parent company, and Virgin Orbit ceased to exist as a going entity a few months later. The epilogue to this chapter came a couple of months before I posted this video. The UK Space Agency did a tour of various UK cities with a pop-up learning centre for kids and a scale model of a rocket. Of course, I was excited to take my son along. Now, this footage was taken as they were packing up. It didn't actually look this sad when they had everything set up. But look at the rocket. It's Launcher 1. Why do we do this? We inspire our youth by parading our failures in front of them. Due to the political reasons I discussed earlier, I think there's zero chance of a UK government-funded space programme for decades. But there is now a ray of hope for the next best thing: private spaceflight. In the past few years, the UK Space Agency have supported the construction of a number of spaceports. It does seem a little odd how we went from 0 to at least 5 of them. In my opinion, only 2 of them are of real interest. The first is Saxavord, situated on the northern extremity of the northerlymost region of the UK, the Shetland Islands. The project faced headwinds as it's situated on an old World War II radar site, and it was objected to by Historic Scotland. This is a regulatory difficulty for doing anything in the UK. It's surprisingly easy to halt construction projects here by lodging oppositions. And this isn't always a bad thing. It can be quite democratic, as it does give residents some power to stop unwanted developments by giant corporations, for example. However, in so many cases, it really does just look like innovation being stamped out by excessive regulation. I was ready to include a section here spitting fire about our past stopping us moving into the future. However, Historic Scotland quickly dropped their opposition, recognising the value of the project, so credit to them. A major proposed customer for Saxavord is Skyrora. Based in Edinburgh, Skyrora have certainly been the frontrunner in the media for the first privately funded British launch to orbit. And I do have to say, I'm pretty optimistic about them. Very much a spiritual successor to Black Arrow, their XL launcher, currently in development, is a light launch vehicle intended to put a payload of up to 315 kilos into low Earth orbit. What I find particularly exciting about Skyrora, they intend to use kerosene and peroxide as their propellant, just like Black Arrow. So finally, 50 years after it was abandoned, perhaps the hard work of the Black Arrow team won't go to waste. Even more exciting, remember how I discussed the open cycle of the Black Arrow engines? Skyrora have closed the cycle. Their engine feeds decomposed peroxide back into the combustion chamber. So maybe they'll be able to use the HTP kerosene cycle to its full potential. They even retrieved a spent Black Arrow first stage from the Australian outback and brought it back to the UK. And they've floated proposals to retrieve Prospero and bring it back to Earth. The second nascent UK launch provider, also based here in Scotland, is Orbex. They seem to be slightly less progressed than Skyrora, though that may not be true, as both companies are currently keeping development quite under wraps. Orbex are also working on a small sat launcher, Orbex Prime, targeting 180 kilos to low Earth orbit. This will uniquely use propane as the fuel, housing it in concentric tanks with the oxidizer. Orbex also state they're targeting a reusable first stage for their platform. Orbex plan to launch from the currently under construction Sutherland spaceport on the north coast of Scotland. Though extremely remote, you can bet I'll try my damn hardest to go and film the launch and post a video when that happens. I think a few individuals have completely sullied the image of privately funded spaceflight to the general public, with many viewing it as a midlife crisis for billionaires. But we shouldn't forget there are plenty private companies already that just launch rockets without the drama, and do a good job of it. And I'm excited the UK may soon finally join the game. Both Skyrora and Orbex have modest yet realistic goals, and I wish them both the best. Prospero is still in orbit. You can see it on a clear night with a pair of binoculars. Its main radio transmitter was functioning until at least 2004, with some reports even stating it was still detectable in 2011. It stands alone as a monument to decades of government apathy to scientific research and innovation. My hope is that the next generation of UK scientists and engineers will not have to face the depressing headwind of ambivalence that has plagued the sector for decades. And one day, maybe quite soon,
7, 6, 5, 4, 3, 2, 1, blast off.